subtopic is solution to first order linear differential equation. Now, we know that first order linear differential equation is of the form divide the x plus y, or call here a of xy is equal b of x. This is equation 1. Now, multiply 1 through by b of x, we will have b of x divide the x plus b of x, a of xy is equal b of x, b of x. Now let's put p prime of x is equal p of x times f of a of x. You see this place now. We want to put p prime of x is equal here. Now call this one equation 2. If we put that, we will have p of x divide the x plus p prime of x y is equal b of x, b of x. Now we see that this place automatically become d dx of b of x, y, which is equal b of x plus, b of x, b of x. Now see, this one is, if you differentiate this place, d dx of this, if you differentiate this by product rule, you get back everything here. That is the meaning of this place. Because, with product rule in elementary differential equation, elementary calculus, you see that if I have something like this, I will keep p of x, then differentiate y, plus I will keep y, differentiate p of x. So this one becomes this. Now, if I integrate here, if I integrate both sides, I will have p of x, y will be equal integral p of x, b of x. Okay. And this become the solution. The x, because I'm integrating with respect to x. So this becomes the solution to first order linear differential equation. But let's see how we can obtain the integrating factor. Obtaining the integrating factor. We now look at 2. We call from 2. We call from 2 that p prime of x is equal p of x times a of x, which is the p all over the x. P prime of x is the same as the p dx. So I can then write that the p dx is equal p of x times a of x. Can write like that this is equal this. Which I can also write that the p dx is equal p a of x. If I use this to times it, I'll get back. Now by separation of variable, the separation of variable which we have learned from the starting of these lectures, we talk about separation of variable. We can write here as if p all over p is equal ax dx. Now integrating both sides, we have ln p will be equal integral of ax dx. If I take log of both sides, take logarithm of both sides. If I do that, I will have that p is equal exponential integral a of x dx. Now, this one is the integrating factor. So what it means is that if you are given a linear differential equation to solve, the first thing we will do is to look at how we can derive the integrating factor. What is the integrating factor? Now we compare this with the first order differential equation that we said it is of that form. It is like this: dy dx plus a of x y is equal b of x. Now if you are given this type of equation, you see that integrating factor will be exponential raised to a of x. So if we are given the equation, the first thing we'll do is to look at this place. Look at here. What is there? And then whatever is there is what we will use as integrating factor. We raise that thing now, we raise exponential to whatever is here. And then we integrate it to have the integrating factor. Example will help us to understand better. So let's pick example. So let's look at these examples. Solve dy dx plus 2xy is equal 5 exponential minus x squared. Y of o is equal 3. Now this is called initial value problem. I'm going to show you how you do that. Then number 2 is x divided x plus y is equal x cubed. This is all linear differential equation. Okay, so we pick the solution of the first equation, which is y dx plus 2xy is equal 5 exponential minus x squared. Now here, let's recall that integrating factor is given by exponential integral a of x dx. This is what we derive as our integrating factor. So now, a of x in this equation is here is 2x. This is where we have 2x, this place. So what we'll do now is to raise 2x and say exponential integral 2x. Look at that. Dx, which will be exponential. If you integrate this, integrate 2x, you have x squared. Look at that. Because here will be 2 over 2, so you have x squared. So this is our integrating factor, exponential x squared. Now if you have this, the next thing is to multiply through by integrating factor. That was how we showed the proof. Now we are going to multiply. Multiply through by integrating factor, which is equal exponential x squared. That is our integrating factor, exponential x squared. This. So if we multiply this through, we will have exponential x squared dy dx plus 2x y exponential x squared is equal 5 exponential minus x squared times exponential x squared. We now see that this place is the derivative. The derivative of y times exponential x squared will give you this. If you differentiate this, that is, we keep exponential x squared, we differentiate y, plus we keep y, we keep this y, and we differentiate exponential x squared. So this is the derivative. Now this place, according to law of indices, this, if we add the power, we have 0. Anything raised to 0 is 1. So here remain only 5. And what we'll do now is to integrate both sides. If we integrate here, we have y times exponential x squared will be equal integral 5 dx. We are integrating both sides with respect to x. Of course, this. By the time this is the differential of this, so when you integrate here, you get, what we are integrating is here now, because the differential of this is this. So integrating here, we'll get back this inner function in this place with respect to x. And if we do that, we'll have that y exponential x squared is equal to 5x plus c. Now, this is where the initial value problem comes in. We recall that y of o is equal to 3. Now, what it means is that, y of o here is anywhere x is, we'll be putting 0, mean y of 0. So, I will have 3 exponential 0 squared will be equal 5, 0 plus c. Now this will give us 3 is equal c. So c is 3. So we can now go back to this place and write that y exponential x squared will be equal 5x plus 3, which means that y will be equal 5x plus 3 divided by exponential x squared. Or we can write that y is equal 5x plus 3 exponential minus x squared. So that becomes the solution. It's very simple to follow. So let's look at solution number 2. We have that x dy dx plus y is equal x cubed. Now, the first thing we'll do is to divide through by x so that we can have it in the proper form of linear differential equation. So divide through by x, we'll have that dy dx plus y all over x is equal x squared. If you divide through by x, it's going to become x squared. Right. Now here, we have to recognize our integrating factor. We have to recognize that in this particular equation, integrating factor is given by p is equal exponential integral ax dx. So we have to know that ax, this function ax, here in this particular equation is 1 over x. So in this equation, the integrating factor becomes exponential integral 1 all over x dx, which is the same as exponential ln x. And so exponential ln of x will be equal x. That is integrating factor x. And so we are going to use that to multiply this equation. If we use it, we now have that x dy dx plus y is equal x cubed. We are getting back the other equation. And we see that this is the same thing as having y or having d dx of xy is equal x cubed. If you differentiate this place xy, that is, you keep x, you differentiate y, plus you keep y, you differentiate x. So this place here is the derivative of this function. That is, you differentiate this, you have this. Now integrating both sides with respect to x, we will have xy will be equal integral x cubed dx, which will give us, if you integrate this, you have x raised to the power 4 all over 4. Okay. Plus c. So we have here that xy is equal this. The next subtopic is Bernoulli's equation. An equation of the form dy dx plus axy is equal b of x y raised to n is called Bernoulli's equation. Method of solution. Look at the method of solution, how we can solve Bernoulli's equation. Bernoulli equation is of this form, which we know. A of x, y is equal b of x, y raised to n. Now, we are going to divide through by y raised to n, because this is what makes it Bernoulli equation. From the linear equation that we just finished, you see that from here to here is the same. It's only this one, y raised to the power n, that makes it Bernoulli equation. So we'll divide through by y raised to the power n. Then we'll have y raised to minus n dy dx plus a of x y raised to 1 minus n will equal b of x. Now how? Because if I divide here by n, I'm just taking y up, that is y raised to n. So I'm just taking it up. Of course, if I take it up, I will have y raised to negative n. Same thing happened here. Here I have y. Look at, I have y. In this place I have y. So if I divide by y raised to n, and if I take it up, I will have y times y minus n. According to law of indices, I can pick one, which is y raised to n. So that is how I got this place. Alright. Now, if I have that, I'm going to let z is equal y raised to 1 minus n. Let z be that. So that dz all over the x will be equal, if I differentiate this, will be equal 1 minus n y raised to minus n. You know how? Because if I differentiate this is coefficients according to formula, according to formula in differentiation. If I use this, as according to formula method, if I use this and times the coefficients, I will minus 1 So if I have 1 minus 1, so this will go. So it remains minus n. That is how I have here. dy dx. So the z dx is equal to 1 minus n y raised to minus n dy dx. Okay. Now, I'm going to substitute this in this equation. If I put this in this equation, I will have y. You see, this is dy dx now. This is dy dx. So let me multiply this by 1 minus n. That is multiply. Let me name this equation 2. This is 1. So multiply 2 by 1 minus n. And then I will have 1 minus n y raised to n dy dx plus 1 minus n a of x y raised to 1 minus n will be equal b of x. Now we see that we have been able to convert this. See, 1 minus n y raised to minus n dy dx, which is equal the z dx. So we can write here the z dx, because the z dx is equal this. Now, plus 1 minus n a of x z. How? Because z is y raised to 1 minus n. So we can just put z there, which is equal b of x. Now observe that the equation is now linear in z. So this equation now is linear in z. So that is the method that we use in solving Bernoulli's equation. So let's pick example. Example will show and will let us understand it better. So let's look at this example. We are asked to solve dy dx plus y all over x is equal 3x squared plus 16 times y raised to the power 4. Now this equation is Bernoulli's equation because of y raised to the power 4. And so, by our method of solution, if we have dy dx plus y all over x is equal 3x squared plus 16 times y raised to the power 4. We are going to divide through by y raised to the power 4. And then we will have y raised to negative 4. I've told you that I'm dividing by y raised to the power 4. So taking it up, I will have like this. Plus, now here, I'm dividing by this. I'm dividing by y raised to the power 4. Of course, that will be y all over x times y raised to the power 4. And this can cancel. This y can cancel 1y. And I will have y raised to negative 3. Yes, all over x. That is what I will have there. You know, what is there is y all over x divided by y raised to the power 4, which will give us y all over x, y raised to the power 4. So this one can cancel and also cancel 1y here, which we have 1 all over x raised to the power 3. So taking this up, we will have y raised to minus 3 all over x. Okay. Then this place, now we have divided it by y raised to the power 4. So what we have here is 3x squared plus 16. That's what we have. Now, let let z is equal y raised to negative 3. In our method of solution, we say let z is equal y raised to 1 minus n. N in this context is 4. So 1 minus 4 gives us minus 3. And so we have that z is this. So that the z all over the x will be minus 3y raised to negative 4 dy dx. You know why we have negative 4? Because when we differentiate this, we have minus 3, then minus 1, it was minus 4. Okay, now we are going to multiply. Multiply with this one. Let's call this equation 2. This is 1. So multiply 2 by minus 3, by this coefficient. Because by the time we multiply that by these coefficients, we will convert it to the z dx. So if we do that, we have minus 3y raised to negative 4 plus minus 3y raised to negative 3 all over x will be equal minus 3x squared plus 16. So we are multiplying everything here by minus 3. And if we have that, okay, minus 3y raised to negative 4 dy dx. Yes, minus, because this place will become minus now. Minus and plus. So we become minus this. And we can write this as dz all over the x. Dz dx is minus 3y raised to negative 4 dy dx. Minus 3 raised to negative minus 3y raised to negative 4 dy dx. So that is the z. Minus 3z all over x. You know why we say z? Because z is minus y raised to minus 3. Look at z, y raised to minus 3. So we put z, which is now the same as minus 9x squared minus 3 times 16, that is minus 48. Yeah, minus 48. So we have that. Now, we see that this equation is now linear differential equation. We have converted it from Bernoulli to linear differential equation. And so, we have to recognize our integrating factor. Integrating factor P will be equal exponential integral a of x, like we derive the x, which is exponential integral, which place is taking a of x. A of x is minus 3 over x. Because this z is like y, that kind of, we're doing function of y. This one is function of z now. So we see that minus 3 all over x is the coefficient of z. Okay, so we have minus 3 all over x dx. Of course, if we integrate this, we'll have exponential minus 3 ln x. We bring out minus 3, we have 1 over x. So we ln x, which is the same thing as exponential ln x raised to minus 3. By logarithm, we can carry this to this power. An exponential ln of function will be equal function. We know that. So we have only x raised to negative 3, which is the same as writing 1 all over x cubed. So, the next thing is to use our integrating factor and multiply this as usual. So we now have 1 all over x cubed, the z all over the x. Then we'll tie this. We'll have minus 3z all over x raised to power 4. When we tie this, we have x raised to power 4. Then we have minus 9x squared. You know how? Because x squared, okay, this is x raised to power 3. Okay, we'll have We have only x here because x all over 3. We have x squared all over x cubed. And then 2 here will cancel here, remaining 1. Minus 48 all over x cubed. That is what we will have. And then we find out that this side become ddx. ddx of 1 all over x cubed z. If you differentiate this, you get the whole thing here. That's what it means. Will be equal minus 9 all over x minus 48 all over x cubed. Okay. Now let's integrate. Integrating both sides with respect to x. To do that, we have 1 all over x cubed z is equal, if you integrate here, we have minus 9 ln x. Now let's integrate here. Before we do that, we have minus 48 x raised to power 3. So if I integrate here, I will have minus 9 ln x. You know, this one will times here. This one will times here. And if that one times here, we have 48 times 3 will give us, this time this is 24. Carry 24, carry 2. This time here will give us, this will give us what? 3 times this 12 plus this 14. So we have plus, okay, this is what we have. This is what we have. So integrating it now will be minus 48, yes, x, sorry, minus 48x raised to negative 2 all over negative 2. You know how? It's integration, not differentiation. So we have to add plus 1 and you reduce it to minus 2, and the downside will be minus 2. So you see that this can cancel this. Sorry, so we have minus 9 ln x plus, of course, 48 divided by 2 will give you 24 plus 24x raised to negative 2. Yeah, that is what we have here. X raised to negative 2. So z all over x cubed, z all over x cubed, that is this times this, will be equal to this, which we can also write this as minus 9 ln x plus 24 all over x squared. It's still correct. It's still correct. So, which means by cross multiplication, look at, by cross multiplying this, we can have it in this way, that z is equal x cubed minus 9 ln x plus 24, yes, plus 24 all over x squared. Z is equal that. Now, but z is equal y raised to negative 3. You know, that is from here. Z is equal y raised to negative. So we have to convert it again to y. So z is this, which means we can write it as y raised to negative 3 is equal x cubed minus 9x plus 24 all over x squared. You can write it that way. Which the same thing is 1 all over x cubed is equal x cubed, 1 all over y cubed is equal x cubed minus 9 ln x plus 24 all over x squared. Okay. Now, how do we see this? Because we need y. We need y. And so what we do is by cross multiplication, by cross multiplying this and going this, we see that this will times this and this will times this. So at the end of the day, we have that y will be equal 1 all over cube root. You know, y will become y cube, which is joined by this. So we make y cube solid or the formula. Okay. We have x cubed minus 9 ln x plus 24 all over x squared. Alright, plus c. So that is how we can solve it, and it is very simple to follow based on your knowledge of elementary differential calculus. So you can understand that this thing is very simple to deal with.